So let's kind of go over an example, and we'll actually use the aluminum hydroxide to go through a calculation. So the calculation we're going to be asked is we want to calculate the molar solubility of AlOH3 as a solid in 15 molar ammonia. So we're going to come up with a method or a way to look at each one of these solubility problems. And what I'm going to do is I'm going to step back a second, and before we try to attack this particular problem, I really want you guys to try to understand what's happening at a molecular level. So in order to approach this problem, we're looking at the solubility of aluminum hydroxide. So if you have AlOH3 as a solid, and we have that in aqueous solution, we're going to set up an equilibrium between Al3 plus in aqueous solution plus 3 OH minus in aqueous solution. So let's think about how we can manipulate the solubility of this particular problem. We have an equilibrium established. We know that we can apply some type of a stress onto this particular equilibrium to see what's going on. So we can say that adding or neutralizing OH minus will change the solubility. We also need to keep in mind that adding or removing the Al3 plus will change the solubility. So there are definitely two things that we can do in this particular case. The question that we want to ask ourselves is, what will NH3 do to the concentration of aluminum 3 plus and the concentration of OH minus? So we ultimately have to always keep this in the back of our mind, not for this particular problem, but for any type of problem where we're trying to perform a solubility calculation. So what happens to these concentrations when I add a particular reagent? One of the things that we also have to keep in the back of our mind is that ammonia is a weak base. So what's going to happen here is we're not just adding NH3. Remember that since we have an aqueous solution, if I'm adding the ammonia to that solution, we have NH3 in an aqueous solution plus water is going to form an equilibrium to give us NH4 plus OH minus. So don't forget that the ammonia will form this equilibrium, and by adding ammonia, we are furnishing this equilibrium with OH minus ions. There's going to be a Kb expression, so we're going to get a particular concentration of OH minus. By adding 15 molar ammonia, that does not mean we have 15 molar hydroxide ions. Remember, there's a Kb associated with this particular equation, but we are going to get a small amount of the OH minus ions. So this is why in some cases we have to add such a high concentration of ammonia to get the amount of hydroxide ions that we want. So when we add ammonia, we're not just having NH3 in that solution. We also have NH4 plus and we have OH minus. So now keeping all of this stuff in the back of your mind, Another thing that you have to look at, so step number 1 is usually to write out the equilibrium expression. Think about all these things that we just stated. Then step number 2 is to look at the KF tables. And the reason we look at the KF tables is because we need to determine if a complex ion will form from the species in solution. And ultimately, we didn't go through these first 2 steps in the very beginning, but when you go through and you solve these problems, you need to keep these 2 in your mind right now. Because we wanted to start kind of slow with this common ion formation, then introduce pH effects, then introduce complex ions. Now we're painting the entire picture by looking at these special cases that we refer to as amphoteric complexes. And this will allow us to properly, take everything into account when we're dealing with solubility. If we look at the KF tables, we will see that Al3 plus does not form a complex ion with ammonia, but it does form a complex ion with the hydroxide ion. So we have Al3 plus 4 OH minus is going to be in equilibrium with AlOH4 minus, and this is going to have a KF value equal to 7.7 times 10 to the 33rd power. Holy crap, that's huge, right? 7.7 times 10 to the 33rd. What this is telling us is that this reaction probably would be better suited to be right as a full arrow going over to the right. Because with such a large KF value, predominantly the products are going to be present. One of the things is, though, we have a 1:4 ratio of the aluminum to the hydroxide ions. So the question is, what do we have going on in solution, and how can we tie all these effects together to see what's going on? So I'm going to draw a little beaker here, and initially we're going to put aluminum hydroxide, which is AlOH3, in equilibrium with aluminum 3 plus 3 OH minus ions. And we're going to assume this is an aqueous solution. So if we have an aqueous solution of this stuff, what we're going to have present is, I think the KSP for this particular reaction has like 10 to the minus 33 for its K. So we're going to have a lot of aluminum hydroxide solid down here. That's going to be in equilibrium with aluminum 3 plus ions and OH minus ions. So our species that's present right now in our beaker is solid aluminum hydroxide, a lot of that at the bottom, and it's going to form a small amount of aluminum 3 plus ions and OH minus ions in solution. We're going to add NH3. When we add NH3, remember from back at that equilibrium, the species that are going to be present, and when I say add NH3, a light bulb should go in your mind, and what you should be thinking is, by adding NH3, it's going to set up an equilibrium where we're going to have NH3, we're going to have NH4 plus, and we're going to have OH minus added to this solution now. So if we add a large concentration of this stuff, we now have our aluminum hydroxide solid down here. So here we have AlOH3 as a solid. It's going to be in equilibrium with the species above it. So here we have aluminum 3 plus and our 3 OH minuses. So the ions that are in this solution are the 3 OH minuses and the aluminum 3 plus. But now we add the ammonia. So what that's going to do is it's going to produce OH minus ions, it's going to produce NH3 ions, and it's going to produce NH4 plus ions. The thing that's going to happen here is we're going to form a complex ion. So our complex ion forms from aluminum 3 plus interacting with 4 OH minuses. So what happens is, and I'm going to throw some extra OH minuses in here to kind of prove the point, we get a complex ion that forms between the aluminum and 4 of these ions in solution. So think about, as we're going through all these steps, how this is going to influence the solubility. Because what we're doing by forming this complex ion, we are dropping the concentration of the aluminum 3 plus, and we are also dropping the concentration of the OH minus. So our initial equilibrium that's established right up here, where we have aluminum hydroxide as a solid with aluminum 3 plus ions in solution and 3 OH minus ions in solution, if we drop the concentration of both the aluminum 3 plus and the hydroxide minus, that's going to shift this equilibrium to the right. So what's going to happen is that we have to take some of these solids and they're going to be pumped back up into solution. So that means the AlO3 solid is going to dissolve. So AlO3 is going to dissolve when enough NH3 is added. So in this particular process, what we want to do is, if I wanted to dissolve all of that aluminum hydroxide, I would add excess ammonia and I would add it in high concentrations. So if we want a particular substance to dissolve, we're going to use the concentrated ammonia that's in the side hood in the glass bottle, and we're going to make sure that we add enough of that to dissolve. Because the moment that this aluminum comes into contact with any of these hydroxides, since this Kf right here is so high, it's going to immediately form a complex ion. And that will drastically influence the solubility. So when you're analyzing problems that are dealing with solubility, you need to approach them as you would if they're amphoteric in every case. Because if you use that train of thought, you can solve any solubility problem. The next step is to take this aluminum hydroxide solution, add 15 molar ammonia, and do a calculation to figure out when everything dissolves and the concentrations that you have. So we will pick up with that on Monday.